You just learned about an exciting clustering algorithm that's really easy to implement called k-means. To give you the algorithm in pseudocode, initially we select k cluster centers at random, and then we repeat. In a correspondence step, we correspond all the data points to the nearest cluster center, and then we calculate the new cluster center by the mean of the corresponding data points. We repeat this until nothing changes anymore. Now, special care has to be taken if a cluster center becomes empty. That means no data point is associated, in which case we just restart cluster centers at random that have no corresponding points. Empty cluster centers restart at random. This algorithm is known to converge to a locally optimal clustering of the data points. The general clustering problem is known to be NP-hard, so a locally optimal solution, in a way, is the best we can hope for. Now let me talk about problems with k-means. First, we need to know k, the number of cluster centers. As I mentioned, they're local minima. For example, for 4 data points like this, and 2 cluster centers that happen to be just over here, with a separation line like this, there will be no motion in k-means, even though moving one over here and one over there would give a better solution. There's a general problem of high dimensionality of the space that is not dissimilar from the way k-nearest neighbors suffers from high dimensionality. And then there's a lack of a mathematical basis. Now, if you're a practitioner, you might not care about a mathematical basis, but for the sake of this class, let's just care about it. So here's a first quiz for k-means. Given the following 2 cluster centers, C1 and C2, click on exactly those points that are associated with C1 and not with C2. And the answer are these 4 points over here. And the reason is, if you draw the line of equal distance between C1 and C2, the separation of these 2 cluster areas falls over here. C2 is down there, C1 is up here. So here's my second quiz. Given the association we just derived for C1, where do you think the new cluster center C1 will be found after a single step of estimating its best location given the associated points? I give you a couple of choices. Please click on the one that you find most plausible. And the answer is over here. These 4 data points are associated with C1, so we can safely ignore all the other ones. This one over here would be at the center of the 3 data points over here, but this one pulls back the center point drastically towards it. This is about the best trade-off between these 3 points over here that all have a string attached and pull in this direction compared to this point over here. Any of the other ones don't even lie between those points and therefore won't be good cluster centers. The one over here is way too far to the right. In our next quiz, let's assume we've done one iteration and the cluster center of C1 moved over there and C2 moved over here. Can you once again click on all those data points that correspond to C1? And the answer is now simple. It's this one over here, this one, this one, and this one. And the reason is the line separating both clusters runs around here. That means all the area over here is C2 territory, and the area over here is C1 territory. Obviously, if we now iterate k-means, this cluster center will move straight over here, where it will stay, whereas C2 will end up somewhere over here. So let's now generalize k-means into expectation maximization. Expectation maximization is an algorithm that uses actual probability distributions to describe what we're doing. And it's in many ways more general, and it's also nice in that it really has a probabilistic basis. To get there, I have to take the discourse and tell you all about Gaussians, or the normal distribution. And the reason is, so far we just encountered discrete distributions, and Gaussians will be the first example of a continuous distribution. Many of you know that a Gaussian is described by a density that looks as follows, where the mean is called mu, and the variance is called sigma, or sigma square. And for any x along the horizontal axis, the density is given by the following function. 1 over square root of 2 pi times sigma, and then an exponential function of minus a half of x minus mu square over sigma square. This function might look complex, but it's also very, very beautiful. It peaks at x equals mu, where the value in the exponent becomes 0, and towards plus or minus infinity, it goes to 0 quickly, in fact, exponentially fast. The argument inside is a quadratic function, the exponential function makes it exponential, and this over here is a normalizer to make sure that the area underneath sums up to 1, which is a characteristic of any probability density function. If you map this back to our discrete random variables, for each possible x, we can now assign a density value, which is the function of this, and that's effectively the probability that this x might be drawn. Now, the space itself is infinite, so any individual value will have a probability of 0. But what you can do is you can make an interval, a and b, and the area underneath this function is the total probability that an experiment will come up between a and b. Clearly, it's more likely to generate values around mu than it is to generate values in the periphery somewhere over here. And just for completeness, I'm going to give you the formula for what's called the multivariate Gaussian, where multivariate means nothing else but we have more than one input variable. We might have a Gaussian over a 2-dimensional space or a 3-dimensional space. Often these Gaussians are drawn by what's called level sets of equal probability. Here's one in a 2-dimensional space, x1 and x2. The Gaussian itself can be thought of as coming out of the paper towards me, where the most likely or highest point of probability is the center over here, and these rings measure areas of equal probability. The formula for a multivariate Gaussian looks as follows. N is the number of dimensions in the input space. Sigma is a covariance matrix that generalizes the value over here, and the inner product inside the exponential is now done using linear algebra, where this is the difference between a probe point and the mean vector mu transposed sigma to the -1 times x minus mu. You can find this formula in any textbook or web page on Gaussians or multivariate normal distributions. And it looks cryptic at first, but the key thing to remember is it's just a generalization of the one-dimensional case. We have a quadratic error over here as manifested by the product of this guy and this guy. We have a normalization by a variance or covariance as shown by this number over here, or the matrix, inverse matrix over here. And then this entire thing is an exponential form in both cases. And the normalizer looks a little bit more different in the multivariate case, but all it does is it makes sure that the volume underneath adds up to 1 to make it a legitimate probability density function. For most of this explanation, I will stick with one-dimensional Gaussians. So all you have to do is to worry about this formula over here. But this is given just for completeness.